Hello and welcome back. In 3.4 we look at the idea of equivalent statements. They were nice enough to give us a little preview of that on one of the 3.3 problems. So first, a definition: two statements are equivalent if they have the same truth values. So in other words, for the whole table, the symbol looks kind of like the biconditional, except instead of a single arrow, it's with two ends, it's a double arrow with two ends. So for example, is not Q implies P and R, equivalent to the statement negation of P and R implies Q. So to find that out, we need to make truth tables for both of these statements and check if the 8 rows, in this case 8 rows because we have 3 simple statements, if the 8 rows are the same in each case, then they are equivalent. If there's even one difference in one of the 8 rows, that's enough to say not equivalent. So I would even say, just for practice, go ahead and make your 8-row start for the truth table and then unpause it and we'll finish it out together. Hey, welcome back. So again, just our little true, 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 false, false, true, false, false, preceded by true and false. Okay, so for the left-hand side, we'll take a look at what not Q looks like. So not Q, negation of Q, we switch truth values. So true, true becomes false, false. False, false turns into true, true. And then that happens again. P and R. Remember, with the and, the conjunction, we need both parts to be true, otherwise it's false. So row 1, we're okay. Row 2, because of R, we're false. Row 3 is true. Row 4, because of the R, we are false. Rows 5 through 8, because of the P, is automatically false. So I'll try a not Q implies P and R. And those are right in a row, so I don't have to kind of draw you any arrows of where I'm looking. So false followed by anything is true for the conditional. False followed by anything is true. True followed by true is okay. True followed by false. So remembering back to our kid analogy, the kid cleaned the room. You said if you clean the room, we'll go to the park, and you didn't go to the park. You did tell a false statement there. False followed by anything is true. True followed by false is false. So when we finish this one, if each of these is exactly the same in the same row, then they are equivalent. If not, these two are not equivalent. So let's see. So we already have a P and R. So we already have that column. So all we need now is a negation of that. So negation of P and R. So negation, remember, just flips our truth values on us. And we already have a Q column, so I'll just kind of draw the arrow to which two columns we're looking at. Those are in a little tight. I might even circle them up just to help out. So negation of P conjunction R implies Q. So this one, if we have a true in this column, a false in that column, that would be false. Anything else will be true. So false followed by anything is true. For the if-thens, true followed by true or okay. False followed by anything is true for the if-thens. So true followed by false, that is false. True followed by true is okay. True followed by true, we're okay there. True followed by false is false. True followed by false is false. So now we want to see if this turned out exactly the same as this in row by row. So true for row 1, true for row 2, true for row 3, false for row 4, true for row 5, true for 6, false for 7 and 8. Every single one of them was exactly the same. So are they equivalent? Yes, they are equivalent. Again, if even one row, if the first 7 were matched exactly, but this one was false and this one was true, the answer would be a no. So even one row off is enough for 2 statements not to be considered equivalent. Okay, so I'm going to have you all try one on your own. Let's see, so I'll have you try P or Q and R. And we want to know, is that equivalent to not P implies Q and R. So go ahead and pause it, unpause it when you're done and ready to see the solution work through. Okay, welcome back. So P's, Q's, and R's. 3 simple statements, so 2 to the 3rd or 8 rows. And again, just based on that first simple table. Okay, so left-hand side, it looks like we need a Q and R. For the conjunction, we need both parts to be true. If I tell you I am a teacher and an astronaut, I have lied to you. If I said I am a teacher or an astronaut, I've told you the truth. This one is an and. So an and, both parts need to be true. In row 1, we're okay. Row 2, because of R, we are false. Row 3, because of Q, we're back to false. Row 4, we go if both times. Row 5, though, true, true, we're okay. 6, 7, and 8 each have at least one false in them. Now we'll union that with P. So remember, with the or, if I tell you I am a teacher or an astronaut, I've told you the truth. So either one is true. The whole thing is true with the disjunction. So that means automatically from column P, the first four are freebies. They're automatically true because P was true. After that, if this column comes through, we're true. But row 6 here, they're both false. 7, both are false. 8, both are false. So this is what we're hoping that the last column of the right-hand side looks like when we're done with it. Let's see, a quick not P column, 4 false, followed by 4 true. Q and R, lucky us, we already have one of those. And we're going to start at the not P column and go to the Q and R column with an if-then situation. A conditional. So if not P, then Q and R. False followed by anything is true on the implications. The if-thens. True followed by true, that's also okay. True followed by false is false. So, again, one row at a time. 2 trues, 2 trues, 2 trues, 2 trues, 2 trues, 2 false, and 2 false. They are equivalent. So those two are equivalent to one another. If even one of them is off, the whole thing is off. Alright, so I'm going to have you try one more of these before we start looking at some equivalents that are a little bit shorter and will get us to some nice properties. Okay, welcome back. So this one, you might have noticed we just have P's and Q's, so we can draw a nice small truth table with the 4 rows. True, 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 false, false, true, and false, false. Okay, P conjunction Q, P and Q, true and true is true, true and anything else, true and false is false, false and true is false, 2 falses. So remember the conjunction, both parts have to come through. Next one, we'll need a not P column, so false, false, true, true. Just looking back at the P column. And then we'll connect that one with the Q using the OR. So again, these two guys are pairing up. With the OR, if one part is true, the whole thing is true. False, false, though, is false. True, true, okay. True and anything else with the disjunction, the OR, is okay. So let's see, we have row 1 is the same, row 2 is the same, row 3 is not the same. Happens that row 4 is also not the same, but these are not equivalent. So with the slash through it. We happen to come up with 2 rows that aren't the same, but even one is enough to say that no, it's not. So next we'll start looking at some ones that, again, are very useful in math. We saw these in set theory, De Morgan's laws. There's a logic version to them as well. Negation of P and Q is logical equivalent to not P or not Q. And the negation of P or Q, logically equivalent to not P and not Q. We'll prove the first one together. I'll let you prove the second one on your own. So we'll prove number one. To do that, we just use the truth table. P's and Q's, so just the 4-row will do. So then we find left side P and Q, we'll find that first. As long as both parts are true, an and is true. So the negation of that, we're again just flipping truth values. So a false followed by 3 trues. The right hand side, we need a not P. So for false, false, true, true, we could use a not Q as well. False, true, false, true. And then we'll put them together with an or. So both of them false, end result is false. At least one of them true, the whole thing is true. One false followed by 3 trues both times. That's enough to prove number one. Proof for number two is similar. I'll let you do that one on your own. One more quick proof of equivalent statements. This is not De Morgan's laws, but this is something that is useful for it. You can also show, which is another way to say prove. P is the logical equivalent to the negation of P. That one is pretty short. We only have one simple statement, so 2 to the first 2 rows, a true and a false. So negation of P, true turns into false, false turns into true. The negation of the negation, false turns into true, true turns into false, and sure enough, those two do match. So if you negate a negation, you're back to the original. Almost like in your algebra days where multiplying 2 negatives gave you a positive. The reasoning not quite the same, but just happens to look like what you do in algebra. So let's see, let's do an example with some words in it. So statement P will be the cup is glass. Statement Q will be cup is plastic. So let's do our original statement. Cup is not glass, but it is also not plastic. So first let's translate that into symbols, and then we'll find an equivalent. Not glass, so not P. Remember, but was used similar to and, so this is a conjunction. And it is also not plastic. So use De Morgan's laws. Not P and not Q. Logical equivalent of negation of P or Q. So our equivalent statement it is false that the cup is glass or plastic. So remember, it is false that is saying, okay, I'm going to negate a group, a compound statement in parentheses. Now, using some of the properties from before, we can also write equivalent statements for things that have a negation involving something that had only, say, one negation inside. So we can still use De Morgan's laws. So when we're flipping that group, notice what changed. The quote-unquote sign, the negation, flips. So this one was statement P, so De Morgan will turn that into a not P. That was a not Q, it will turn into a Q. And then look back at De Morgan's laws and see what else changes. What happens to that symbol in the middle? You probably notice each time it flips. So the or will turn into an and. So see if you can write an equivalent statement to let's do negation of not P and not Q. And when you're done with that, see if you can find an equivalent to not P or Q. Again, using the equivalent statement, hint on there, De Morgan's law. Okay, welcome back. So first one started with a parenthesis, so we're basically losing the parenthesis. So again, the signs are going to flip. So this was not P, now it's P. Not Q is going to flip to Q. Our and turns into an or. Similarly on this guy, this time we started without the parentheses. So we would negate a compound statement with that. So not P turns into P, Q turns into not Q, and the or turns into an and you have your equivalent statement. Okay, Some other equivalent statement questions. Equivalent. So I'll try P implies Q, and we'll see, is that the logical equivalent to not P or Q? So go ahead and try that one. Unpause it when you're ready. Welcome back. So hopefully you notice just P's and Q's. So we have our little table this time. True, 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 false, false, true, false, false. So P implies Q. True followed by true, we're okay. True followed by false is the only way to make an if then false. False followed by anything is automatically true for the if thens. So I want to see if this one eventually turns into exactly those truth values. True followed by false followed by two trues. So we'll need a not be column. So false, false, true, true. And we'll union that with Q. One of them is true, the whole thing is true. Both false, the whole thing is false. One is true, the whole thing is true. One is true, the whole thing is true. True, false, true, true. Exactly equivalent. What that gives us also, though, is a way to negate an if-then statement. I'll put an exclamation point since that is an exciting new tool that we have. So for example, if I wanted to negate, we'll just do the basic P implies Q. Then that's equivalent to saying we are negating. We'll swap out P implies Q with what we said it's the same as, not P forward with Q. And then by De Morgan, negation of not P or Q, turn that then into P and not Q. So this is the negation of P implies Q. So let's try negating P implies not Q. So we'll start with what we know. We'll start with this one. The fact that we know that P implies Q is the logical equivalent to not P or Q. So now I want to make it look like what they're asking me about. So I will have to flip this Q to a not Q. If I flipped Q on one side, I'll have to flip Q on the other side. Then we can use De Morgan's law. Oh, my apologies. We're not at De Morgan yet. We have to negate this. So now I want to negate P implies not Q. If I negate one side, I'll have to negate the other side. Now we can apply De Morgan's law. So we started with the star. Look like the question. Negate. And finish it off with De Morgan. So P, not P, turns into P. Or turns into and, not Q, turns into Q. So that is our equivalent. Those two are the same. Okay, so then we finish this section learning some variations on the conditional. So the basic conditional is just P implies Q. Converse of the conditional, we just trade places. Q implies P. Inverse of conditional. So again, I'm going back to the original conditional each time on these. Inverse of the conditional, instead of flipping where the statements are, we just negate each piece. Not P implies not Q. Then we have the contrapositive. We flip both. Not Q implies not P. So I'm going to issue a challenge. Figure out, prove which of the three new conditionals is equivalent to the original. So a little hint on that, you'll need some truth tables for that. All right, so some suggested problems. This is in section 3.4. I would try out 1 through 8 all and 9 to 71 on the odds. If you have any questions, please let me know. Otherwise, I will see you next time. Stay safe out there.